Mr. True, in this lesson we are going to learn about finding limits of functions. The same thing we learned in calculus in chapter 1. And back in chapter 1 we learned how to find limits both graphically and numerically, making a graph of a function and just looking at the graph, maybe using a trace function or the zoom function in our calculator to see a limit, or we found limits analytically by doing those very tedious tables where we let x approach from the left and the right, and we noticed that when the left and right hand limits were equal, the limit existed. And then we learned how to solve or find limits analytically. And that involved algebraically, if needed, manipulating the function to allow us to find, let's say like this example here, a limit as x approaches 2. Well, that's fine, but algebraically manipulating these expressions or these functions isn't always possible, and it certainly is not always the fastest method of finding a limit. So what we're going to do in this video is we're going to see how L'Hopital's rule will allow us to find some limits that we previously were not able to without the aid of a table or a graph. It'll also speed up the process of finding certain limits, and there are many different forms of indeterminate. So in this video we are going to be properly defining L'Hopital's rule and working through 9 examples to help you get through your homework. So, when finding limits, the answers of 0 over 0 and infinity over infinity are called indeterminate. These answers do not guarantee that a limit exists, and if it does exist, there being this, like this example here where x is approaching 2, we do not know what the limit exists. And I have 2 examples up here, but I'm going to move this board out of the way to finish our first page of notes, so let's do this first. Find the limit as x approaches 2 for this rational function where there's a polynomial in the numerator and denominator. And for a lot of functions, if you want to find a limit as x approaches a particular value, you just simply plug it in. Well, if you plug 2 into the numerator and denominator, you're going to get an answer of 0 over 0, which is the indeterminate form. That does not mean the limit does not exist, nor does it tell us, if it does exist, what the limit is. So, and we did these problems earlier in the year, and we don't need a graphical representation of this function or even a table to figure out what the limit is equal to, because I can algebraically manipulate this expression or this function to allow us to find the limit. It's going to be the limit as x approaches 2 of, let's see here, we're going to have 5x and 1x. And if we put a factor of 7 here and a factor of 2 here for our factors of 14, we're going to have 5 times 2 is 10, and 7 times x is 7. We have a middle term which is negative 3x, so the numerator is going to be factored to be 5x plus 7 times x minus 2. And our denominator is going to factor out to be x plus 3 times x minus 2. Well, that common factor of x minus 2 is going to factor out of our function. And in case you forgot, if we were to graph this, that means that this function would have a hole at the x value of 2. But what we do end up with as far as finding limits is we want to find the limit as x approaches 2 of 5x plus 7 over x plus 3. Well, now I have an expression or a function that I can plug 2 into, and we get 5 times 2 is 10, plus 7 is 17, over 2 plus 3 is 5. So we were able to algebraically manipulate this expression so that we can get it out of the indeterminate form and find out what the limit is. So as x approaches 2, the limit of the function y is equal to this rational function is 17 over 5, or there would be a hole actually in this particular case at 2, 17 over 5. But here we have the limit as x approaches 0 of 2 times e to the 3x minus 2 over x. Now if we let x approach 0 here, we are going to get 2 times e to the 3 times 0 power minus 2 over 0, and that is going to come out to be 2 times anything to the 0 power is 1, so 2 times 1 is 2, minus 2 is 0 over 0. Well, that's the same indeterminate form I had with this problem, but there is nothing that I can do with that expression or this function y equals 2e to the 3x minus 2 over x to get it out of this indeterminate form, and that is where L'Hopital's rule is going to help us out. So let me get this out of the way. My high-tech picture-in-picture. We don't have an example anymore, and this is just going to summarize what I said in written words. The indeterminate form cannot be evaluated by algebraic manipulation for this example. When transcendental, that would be in functions, that's an example of that would be e to the 3x. When transcendental and algebraic functions are combined in the same expression, this often is the case where I can't manipulate this out of, algebraically anyway, out of this indeterminate form. So let's get the next page of notes up so we can get L'Hopital's rule defined and learn when we can use it. You can't use it all the time, and one of our examples are going to show when you get in trouble for just arbitrarily using L'Hopital's rule for every single problem. And then, like I said, go through those many examples in the video. Bam! L'Hopital's rule. Let f and b be functions that are differentiable on an open interval ab containing c, except possibly at c itself. Like my algebraic example, functions aren't differentiable at a whole, right? So, and also assume that g prime of x is not equal to 0 for all x in the open interval ab, except again possibly at c itself, because then you'd be dividing by 0. And that's not good. If the limit of f of x over g of x as x approaches c produces the indeterminate form of 0 over 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of c over g prime of c. So, unlike in the previous board where I did that algebraic example, I had to factor the numerator and denominator and see if there was any common factors that canceled. I can just take the numerator and denominator separately and then find the limit of each, and that is the limit as x approaches c of my original function f of x, or expression f of x over g of x. That is going to save us a lot of time. And on that second example that had the transcendental function, that's going to allow us to find the limit, period, where I couldn't with algebraic manipulation. So very powerful. Now, I have this in yellow. I was going to do red, except sometimes it's hard to show up on the camera. This is extremely important. If the limit of f of x over g of x as x approaches c produces the indeterminate form of 0 over 0, and I'll give you some alternative forms on the other side, but if you don't meet the conditions to apply L'Hopital's rule, and you just apply it all the time, it will give you a wrong answer. There's a condition for using this rule. Make sure that you check it. Provided the limit on the right exists, I guess I could just keep reading the thing here, right? Then the limit is blah, blah, blah. Provided the limit on the right, that's this thing right here, exists or is infinite. Now, an infinite limit is not a real limit, but it's still something that we can say, like the function approaches infinity. You know, if a function at c is undefined but approaches infinity from the left and from the right, then the left and right hand limits are equal. Thus, the limit exists, but saying that the limit is infinity is also saying, or infinite is also saying the real limit doesn't exist. But if it approaches infinity from the left and the right, then we do have an infinite limit. It's just not a real limit. This result also applies, and I'm putting this back in yellow again because I want to go back to this condition over here. This result also applies, the result, voila, right there, the actual L'Hopital's rule. If the limit of f of x over g of x as x approaches c produces any one of the following indeterminate forms: infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity. So if you try and find a limit and you get 0 over 0, infinity over infinity, and such, all these other different variations, then you can apply L'Hopital's rule. And note again how this notation reads. You are taking the derivative of the numerator and denominator separately. You are not taking the derivative of the quotient. You're not applying the quotient rule to find the derivative. It is separate, and that's also a common mistake that students make. Now, I've got 4 examples coming up before we start talking about alternate forms or other forms of indeterminate that we have besides the 0 over 0 pattern. That's why I ended up with so many examples. All right, next example. Our first example, coming right up. Our first real example is getting back to that previous example that we could not figure out, not with algebraic manipulation of the function. You'd have to go back to doing a table of values, the numerical approach, or with a graphing utility to find the limit of this function as x approaches 0. But remember, it was 0 over 0, the indeterminate form that says, hey, you can apply L'Hopital's rule to figure out this limit. So let's do it. We're going to find the derivative of the numerator and denominator separately. So we have the limit as x approaches 0 of 2 to the e times e to the 3x. Now that's not just a simple x, like the derivative of e to the u is e to the u du or u prime. So then we're going to multiply by the derivative of 3x, which is just going to be 3. Again, this is all taking the derivative with respect to x, which maybe I should have written since this is the first example. And again, finding that derivative of the numerator and denominator separately. You probably will not want to write that notation and use an extra line of work to write that too many times. But again, it's just a stress. You're not finding the derivative with the quotient rule. It's the numerator and denominator separately. There we go. So the derivative of e to the u is e to the u prime, and that's a constant, so it's 0. The derivative of x with respect to x is simply equal to 1. And now when we go ahead and let x approach 0, we have 2, sorry about that, e to the 0 power times 3 over 1. That comes out to be 1 times 2 times 3 is equal to 6 over 1. And wow, that did not take a whole lot of effort, just making sure that we tried to find the limit. We got the indeterminate form 0 over 0. That says we can use L'Hopital's rule, find those derivatives in the numerator and denominator separately, and boom, just like that, got the answer. Very, very nice process for finding the limit of an expression as x approaches c. Now over here we have the limit as x approaches 0 from the left. So we do have a transcendental function and just some polynomials mixed in together. So let's just see what happens at first. We have e to the 0 power minus 1 minus 0 over 0 to the third power. And that, of course, is going to be 1 minus 1, which is 0, over 0. And I'm putting a check mark, not because I know what the limit is, but I don't know what the limit is. It's indeterminate form, but that 0 over 0, again, says, hey, you can use the L'Hopital's rule to finish this problem up. So that means we have the limit as x approaches 0 from the left. And of course you can see that we can apply L'Hopital's rule to one-sided limits as well, not just two-sided limits. The derivative with respect to x of e to the x is e to the x. The derivative of a constant is 0. The derivative of negative x with respect to x is equal to negative 1. And in the denominator we have 3x squared. So we applied the L'Hopital's rule, we must be ready to go. Let x approach 0 from the left. Well, again, e to the 0 power is going to be equal to 1. So we have 1 minus 1, which is 0, over, 3 times 0, which is, again, 0. So we applied L'Hopital's rule, but what we're seeing here is just, you may not just be able to apply it, or you may not just be able to apply it once, but you might have to apply L'Hopital's rule multiple times. And by the way, there will be examples where you realize that I applied the L'Hopital's rule when it was appropriate, and again I got another indeterminate form, and I applied again, and I applied again, and you realize that you keep applying the L'Hopital's rule, but you still end up with answers which are indeterminate. So there are cases where the L'Hopital's rule won't help you, and you won't know that until you do this process a few times and realize it just doesn't seem to be working out. And we got 9 examples, so let's see if we happen upon one of those problems. The limit, but let's just apply this again. The limit as x approaches 0 from the left. Again, we have that condition that allows us to apply L'Hopital's rule. That's a constant, that's 0. The derivative of e to the x is e to the x, again with respect to x. And down here we have, bringing this power down, we have 6x. Now letting x approach 0 from the left, we have e to the 0 power is again going to be 1. But now here in the denominator, Now we don't have a 0 in the numerator, so I think we're going to have a final answer here. We're going to let x approach 0. Well, 6 times 0 is equal to 0, and we have that 1 over 0 power. Well, as x, as we approach this 1 over 0 type answer or scenario, that is going to approach either positive or negative infinity, and that's where we need to come back in here and realize that we are approaching 0 from the left. So all of our x values must be negative. Now a positive base raised to a negative power, that's really kind of just like e to the negative x is simply going to be 1 over e to the x. It's still going to be a positive answer, or positive 1. But down here, this 6 times a negative answer is going to be, we're going to be approaching 0, but that 0 that we're approaching, all these values are going to be negative down here. It'd be like negative 0.0000001. And then ultimately, so we're looking at 1 over, 0 has no sign, if you will, but that our denominator isn't really becoming 0, it's approaching 0, and it is going to be a negative value. So here our limit is going to be negative infinity. And indeed, if you were to put this into your calculator and draw it, it is going to be approaching, again, negative infinity as you approach 0 from the left, and it'll be going up to positive infinity as you approach 0 from the right. And this isn't the entire function, it's just what's happening as you get close to 0. So if I let that approach from the right, my answer would be positive infinity and not negative infinity. All right? So we got 2 more examples before going on to some other different types of situations using L'Hopital's rule. Bam! For our third example, we have the limit as x approaches infinity of x squared plus x over e to the x cubed. And letting x approach infinity, what do we have? We have infinity squared is a big ol' infinity, and another infinity is another big ol' infinity. And then e, a positive base raised to infinity, is going to be infinity and beyond. So that means that that is a form of the indeterminate that is going to allow us to apply the L'Hopital's rule. So let's find the derivative of the numerator and denominator separately. L'Hopital limit as x approaches infinity of 2x plus 1. Again, finding the derivative with respect to x. And the derivative of e to the u is e to the u times u prime, or du, and the derivative of x cubed is going to be 3x squared. Excellent. Now let's find that limit. The limit as x approaches infinity of 2 times infinity is still going to be infinity. Okay, this is not looking good. And now we're going to let x approach infinity again. Okay, so another one of those problems. Now, what's good? What are we looking at in this example? Well, first, 0 over 0 is not the only indeterminate form that allows us to apply L'Hopital's rule. Again, we might need to apply L'Hopital's rule multiple times. Let's see what happens. We have now the limit, L'Hopital! The limit as x approaches infinity of the derivative of 2x is going to be equal to 2 over, okay, so now before we, let's see here, we have a variable here times a variable here, so we're going to have to use the product rule for derivatives first, times the derivative of the second, which is going to be times e to the x cubed times 3x squared, that's first, times the derivative of the second. We're using that chain rule again, that e to the u, the derivative of e to the u is e to the u times u prime, plus the second, times the derivative of the first, and that is going to be 6x. Cleaning that up, we have the limit, maybe not that we really need to, but the limit as x approaches infinity of 2, 3 times 3 is 9, x squared times x squared is x to the 4th, e to the x cubed plus 6x e to the x cubed. And as you let x approach infinity here, we're going to have 2 over, well, both of these terms have an x in them, right? And that x approaches infinity. So that's going to be some type of infinity plus another type of infinity. So we have 2 over infinity. Well, if the denominator approached 0, right, that means you have a large number, what's effectively over a very, very small number, and that means your function is going to approach infinity or negative infinity. But if your denominator is becoming infinitely large, or becoming, compared to that numerator, which is a constant, that is going to be approaching 0. And let me just make sure I haven't made any mistakes here. Looking good. All right. So for our fourth example, we have the limit as x approaches 0 of 1 plus sine of x over cosine of x. And let's see here. Well, let's just apply the L'Hopital's rule. The limit as x approaches 0, the derivative of 1 is 0, the derivative of sine is equal to cosine. And the derivative of cosine is equal to negative sine of x. As you let x, now remember x is in a trig function, so it is an angle measure, right? So as you let x approach 0, and of course we're talking about positive rotations, right? So as you let x approach 0, the cosine of 0 is going to be equal to 1. The sine of 0 degrees radian, or 0 radians, is going to be equal to 0, but there's a negative out front. So it would appear that the limit as x approaches 0 for this expression is going to be negative infinity. No, it's not. No, it's not. No, it's not. No, it's not. Why? Because just because I'm in a section about L'Hopital's rule doesn't mean every single problem is going to be worked with or be done using L'Hopital's rule. I never checked to make sure that this limit was indeterminate. So if I come back up here and I say, hey, let x equal 0 or approach 0, well, that's going to be 1 plus the sine of 0 is equal to 0, and the cosine of 0 is equal to 1. My answer was 1. My limit was not indeterminate in that indeterminate form, and I just arbitrarily applied L'Hopital's rule and I got the wrong answer. So again, make sure that you check the condition for L'Hopital's rule before you just go on and apply it. Come on, man. Check yourself. Check your problem. Bam! New type of problem or setting. Indeterminate products of 0 times infinity. Now here we have three limits. They all equal different answers. The limit as x approaches 0 of x times 4 over x is equal to 4. The limit as x approaches 0 from the left of x squared times the cosecant of x is equal to 0. And the limit as x approaches infinity of x times the sine of 1 over x, well, that's equal to 1. But if you look at each of these forms, let's get some red here. I think this will be just enough to be able to read. If you let x approach 0, you're going to have 0 times, and then 4 over 0 is going to be infinity. And the limit as x approaches 0 from the left, well, 0 squared is going to be equal to 0. And the cosecant function, that's the reciprocal of sine. And at the xy axis, the sine is at 0, 0, and then goes up to 1 and kind of goes in the opposite direction, approaching negative 1 as you go down to negative pi over 2. So if you think of the sine function getting blown inside out as the cosine function is, I don't know what I'm trying to do with my arms, but the cosecant function as x approaches, I think I said the wrong function there a second ago, the cosecant function as x approaches 0 from the left is going to go to negative infinity. And and then over here we have the limit as x approaches infinity. Well, that's going to be infinity here. And then we're going to be taking the sine of 1 over infinity is basically 0. And the sine of 0 is equal to, again, 0. So all three of these problems are in this indeterminate idea, this indeterminate form of 0 times infinity. So, but yet they all give us different answers. So if the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is either equal to infinity or negative infinity, as we have here, then we do not know the value of the limit as x approaches a of f of x times g of x, or even if it's going to exist. all of these three examples have real limits, but if f is the stronger function, the limit will be 0. If g is the stronger function, then the limit will be either positive infinity or negative infinity, or there may be some finite non-zero answer, some kind of balance between these two functions. Like we had here, there was some kind of balance reached between these two functions. First one going to 0, the second one going to infinity, and they balanced out to be a value of 4. So what you want to do with these problems is you want to rewrite f times g in either format of f over 1 over g or g over 1 over f to convert this 0 times infinity or negative infinity limit that we have into the indeterminate form again of 0 over 0 or infinity over infinity to apply L'Hopital's rule. So we're saying, hey, there's more than just these two, and of course we had those little sign changes there, but of like positive or negative infinity, but there's other forms of indeterminate limits, but to apply L'Hopital's rule, you got to have that 0 over 0 or infinity over infinity pattern or answer in our limit so that we can apply L'Hopital's rule. So, you know what that means? Time for more examples. Woo. Hi, I'm Mr. True, and I just recorded this scene twice because I didn't realize my card was out of memory. I just thought I forgot to hit the record button. Okay, so this indeterminate form of products, take 3, even though it was right the first 2 times. You just didn't get to see it. The limit as x approaches 0 of x times 4 over x. Okay, so we know that this was 0 times infinity, indeterminate form of products, and yet we knew that the answer was equal to 4. So we can rewrite this, we need to try and rewrite this into a quotient which allows us to apply L'Hopital's rule by getting it into that indeterminate form of 0 over 0 or infinity over infinity. So that said, we can take the first or the second factor, flip it down, and so we have the limit as x approaches infinity of 4 over x divided by, again, now that's going to be x over 1, that little bit I just had to erase because I just said this 5 minutes ago. We're going to take that x over 1 and flip it down to be 1 over x. Now, in case you are asking why am I allowed to just flip that down or why does that work? Well, this is one fraction divided by another fraction. And when you divide fractions, you actually have to multiply by the reciprocal of the second fraction. That is going to be the denominator. And thus this would get flipped up and become a multiplication of x over 1. Now, I should be checking to see if I could apply L'Hopital's rule, which then could say, okay, this is an indeterminate form at 0 over 0. Let's find the derivative of the numerator and denominator individually. But in this particular case, the x's just cancel out, and we end up trying to take the limit as x approaches 0 of a constant. So I never even got to apply L'Hopital's rule. This is just the limit of a constant, and of course that is going to be equal to 4. And over here we have the limit as x approaches 0. Oh, yes. You can rewrite this so that you have a division of the reciprocal of either one of these factors. Now sometimes the way you decide to set it up is going to make the problem much easier, or hopefully not harder. So play around with that. With this particular problem, just to show you that it, can work in both directions. I'm sure there's some examples where you really wouldn't want to rewrite it in one particular way over the other. But if I leave this x over 1 in the numerator and take this 4 over x and flip it down to be x over 4, well, now I can take my numerator and denominator and multiply them by 1 over x. That's going to cancel the x's out. We have the limit as x approaches 0 of 1 over 4. And dividing by 1 over 4 is the same as multiplying by 4. And so we still end up again, of course, trying to find the limit as x approaches 0 of 4. Which is still going to be 4. All right, next example. Now, I really probably don't want to take the derivative of cosecant if I don't really have to, so I'm going to rewrite this. So I'm going to divide by the reciprocal of my first factor. And we have the limit we already discussed in the previous screen how all of these are the indeterminate form for products or multiplication. So the limit as x approaches 0 of, oh, excuse me. Yeah, I'm going to leave the, I think I said that wrong. I really don't want to take the derivative of cosecant of x if I don't have to. So I'm going to leave the x squared on top. I believe I just said that backwards. And bring the cosecant down in the denominator. So 1 over cosecant of x. Now, of course, so I've taken the cosecant of x over 1, flipped it down, dividing by the reciprocal. But 1 over cosecant of x is, of course, we know, sine of x. And now, let's make sure that we can apply L'Hopital's rule before we just start doing so without thinking. We plug the x in. We have 0, or the x is equal to 0 or approaching 0. So we have 0 squared, which is equal to 0. And the sine of 0 is also equal to 0. Okay, so that is the indeterminate form now that will allow us to apply L'Hopital's rule. So finding the derivative of the numerator with respect to x. Well, that's going to be 2x. And the derivative of sine is cosine. So the limit as x approaches 0 of 2x over cosine of x. And as we let x approach 0 now, we're going to get 2 times 0 is 0 over the cosine of 0, which is equal to 1. And that is equal to 0. The answer that I said this limit equal to in the previous screen. Now the last one, the limit as x approaches infinity of x times the sine of 1 over x. Well, again, if I bring the sine of x down and divide by the reciprocal, that 1 over sine is going to become cosecant, which may be fine, may work just fine, but why introduce a harder trig function when I don't think that we need to? So we're going to divide by the reciprocal of the first factor, or rewrite this as the limit as x approaches infinity of sine of 1 over x over 1 over x. And trying to find the limit at this point, we're going to have the sine of 1 over infinity is 0, so the sine of 0 is again equal to 0. This is equal to 0 in the denominator, so we are good to finish up by applying L'Hopital's rule. So the limit as x approaches 0 infinity, the derivative of sine is cosine of 1 over x. Now we need to multiply by the derivative of that inside function, that base. Now 1 over x is the same as x to the negative 1, right? And the derivative, let's see, if I'm going to take that negative 1, bring the power down up front, we're going to have negative x, and then we're going to reduce that power by 1. So it's going to be negative x to the negative 2 power. Or negative 1 over x squared. And so down here we have the same thing. The derivative of 1 over x is going to be negative x to the negative 2 power. These negatives are going to cancel out. The x to the negative 2's are going to cancel out. And we end up with the limit as x approaches infinity of the cosine of 1 over x, letting x approach infinity. We're going to have 1 over infinity is 0. The cosine of 0 is equal to 1. And that is the end of these 3 examples, all involving indeterminate form for multiplication or products. Now we're going to move on to indeterminate form of power. Before we move on to the indeterminate form of powers, I just realized, just as I was about to erase the board, that in my frustration of having to shoot this 3 times, when I didn't even make a mistake other than realizing my memory card was getting to be full, to include that little notation that I was approaching 0 from the left. Now, moving on to power. Indeterminate powers if the limit as x approaches a of f of x raised to the g of x power. So you're looking at a function basically, or an expression raised to another expression, yields either 0 to the 0 power, 1 to the infinity power, or infinity to the 0 power. then you can start writing, trying to get that problem into a form that allows you to apply L'Hopital's rule by taking the natural log of both sides of the function. That is going to allow us to then, so we have like, we're going to just basically say, well, okay, let's let y equal f of x raised to the g of x power. We're going to take the natural log of both sides. The power rule for logarithms are going to allow us to take that variable exponent and move it down out front as a multiplication. And then to get the natural log function away from the y, we're going to make both sides of the equation an exponent of y, or just write it into exponential form so that we have e equals y raised, or y, I'm reading this all backwards, y is equal to e raised to the gx times natural log of f of x power, and then kind of see what happens after that. Now this next example is going to be relatively long, so I need to erase this board so I have enough room. Let's find the limit as x approaches 0 from the right of 5 times x to the x over 3 power. If you look at this the way it sits right now, we're going to let x approach 0 from the right. So it's going to become infinitely small, but always be positive. And that means that we're going to have 5 times 0, which is 0, raised to 0 over 3, again a positive 0, approaching 0 but positive 0, if you will, over 3, which is going to be approaching infinity. So we do have that indeterminate form for powers. So I'm going to go ahead and say, let's let y equal the limit as x approaches 0 from the right of 5x to the x over 3 power. And now I'm going to take that 5, because if I'm taking the limit of something with a function or an expression with a constant in front of it, I can pull that out front and write y is equal to 5 times the limit as x approaches 0 from the right of x over raised to the x over 3 power. I want to apply the natural log function to both sides, but I want to get the 5 over to the other side first, just out of just because I believe it's going to be the easiest. So we have y over 5 is equal to the limit as x approaches 0 from the right of x to the x over 3 power. Take the natural log of both sides. We have the natural log of y over 5 is equal to the natural log of the limit as x approaches 0 from the right of x to the x over 3 power. Now because the natural log function is continuous on all values where x is positive, and again we're not letting x equal 0, we're letting it approach 0 from the right, this is a continuous function. So that means that I can take this natural log function and bring it into the limit notation and have the natural log of y over 5 is equal to the limit as x approaches 0 from the right of the natural log of x to the x over 3 power. Now, fix that parentheses there. Normally when I say that I'm going to apply the natural log function or log of any base to a variable, I wrap that inside an absolute value function because you can't take the log of a negative number. But remember, again, we're letting x approach 0 from the right, so x is always going to be positive, and thus the absolute value symbols are not necessary. Now we're going to take this out of this exponential form, so we can write it in this like a, I don't know if it's going to be 0 over 0 or 0 infinity over infinity or whatnot, but to get it into a form which we can apply the L'Hopital's rule, that again that 0 over 0 type idea, we're going to take the x to the x over 3 power and move it out front and get the natural log of y over 5 is equal to the limit as x approaches 0 from the right of x over 3 times the natural log of x. Now if you look at what we have going on here, if we try and apply the limit here, this is going to be infinity, and this, 0, and this is going to be negative infinity. So it's still an indeterminate form, but it's not a form where we can apply the L'Hopital's rule. So we are going to, let's see, how about, I think it's going to be a little bit difficult to sort of write a 1 over natural log type situation. So let's rewrite this multiplication of this x over 3 as a division of its reciprocal and write the natural log of y over 5 is equal to the limit as x approaches 0 from the right of the natural log of x over 3 over x. Now, as we let x approach 0 from the right, remembering that y is equal to the natural log of x, that graph looks something like this. As you approach 0 from the right, that's going to go to negative infinity, and as you approach 0 from the right, this is going to go to positive infinity, which is an indeterminate form where we can use L'Hopital's rule. So, come on, Mr. L'Hopital. We're going to take the natural log of y over 5 is equal to the limit as x approaches 0 from the right. So exciting. The derivative of the natural log of x is equal to 1 over x. And the derivative of 3 over x, well, that's 3 to the x, 3 times x to the negative 1. Using the power, we're going to have negative 3x to the negative 2 power, so it's negative 3 over x squared. Okay, so let's see here. Now if I multiply the numerator and denominator by x over 1, which is effectively just 1, right? These x's are going to cancel out, and that x is going to cancel out with one of those, and we get the natural log of y over 5 is equal to the limit as x approaches 0 from the right of 1 over negative 3 to the x power. And that becomes, well, if you take this bottom and you flip it up, that is going to become x over negative 3, right? I'm running out of room, so I'm going to erase this and rewrite that 1 over negative 3 over x as x over negative 3. And as I let my x approach 0, we get 0. And now that we have the limit as x approaches 0 from the right of x over negative 3 becomes 0, oh, well now I have a format where I can rewrite this back into exponential form. I can take and let both sides be an exponent of e and get y over 5 is equal to e to the 0 power, which is 1. Multiply both sides by 5, and y is equal to 5. And y was the limit as x approaches 0 from the right of 5x raised to the x over 3 power. And let me just double check my notes. We are good. So I got one last form. It's going to be the indeterminate form for differences, and this video will be done with one more example. Thank you for watching. Woo! Love this stuff. Last form, indeterminate form for differences. If the limit as x approaches a of f of x minus g of x equals infinity minus infinity, this is considered indeterminate. If the limit as x approaches a of f of x, which is infinity, if that wins, the answer is going to be infinity. You're going to be taking an infinitely large number and subtracting it with something that's also infinity but not growing as fast, and ultimately that is going to go to infinity. If the limit as x approaches a of g of x, which is infinity, if that wins, if that's the stronger or the larger infinity, if you will, then the answer is going to be negative infinity. Or maybe there's a balance somewhere in between and there's a finite limit, a numerical value. Try to work these out by bringing f of x and g of x together to form some type of quotient. And again, so that way that you, when you get in that quotient form and you try and apply the limit, you get either an infinity over, a 0 over 0, or infinity over infinity, or some form of that with some signs, which will allow you to apply L'Hopital's rule. So our last example, finally, the limit as x approaches 0 of the cosecant of x minus the cotangent of x. Now this time I didn't put a little plus or minus up there on the exponent part to indicate a left or right limit like I forgot to do in the previous example, but this time it was not by accident. If you approach 0 from the right, then your cosecant, you can see this is our graph, or at least one period of a graph of cosecant of x, and we have these, I hope you can see purple lines, 2 periods actually, because well, the period of cotangent is only pi, where the period of cosecant and secant and cotangent, sine and cosine are both 2 pi. At any rate, as you approach 0 from the right, both of these functions are going to infinity. So indeed, this is going to be infinity minus infinity, which is our indeterminate form for differences. And if you let x approach 0 from the left, I want to say negative, but as you approach x from the 0 from the left, as you let x approach 0 from the left, both the functions are going down to negative infinity, and that's going to be negative infinity minus a negative infinity, which is negative infinity plus infinity, which is still infinity minus infinity. So either way you look at it, left or right limit, this is going to have that indeterminate form of of infinity minus infinity. So let's see if we can use this tip here of how to work out these problems and write this in terms of just a quotient. Well, cosecant of x minus cotangent of x, nothing's going to happen there. I mean, there's nothing to do. It's just 2 terms, no common denominators. Oh yeah, that's right. But if I rewrite these trig functions, kind of like doing a trig proof in pre-calculus or trigonometry, if I rewrite this in terms of the most basic trig functions, sine and cosine, I think we're going to have some fractions that we can then use, find common denominators with and combine those. So we have the limit, and again, this is infinity minus infinity. So we have the limit as x approaches 0 of cosecant, which is 1 over sine of x, minus cotangent, which is cosine x over sine of x. And I don't even have to find common denominators. I already have them there, so let's write that as one quotient. We have the limit as x approaches infinity of 1 minus cosine of x over sine of x. And now we just have a quotient. Maybe we can get the answer now, because earlier in the video I did a problem like this and I applied L'Hopital's rule immediately, and I did that when I shouldn't have, because we could find the answer, and L'Hopital's rule gave me the wrong answer. So as we let x approach 0, we have 1 minus the cosine of 0 is 1, so we get 1 minus 1, which is 0, and the sine of 0 is 0. Okay, there we go. We have the indeterminate form of 0 over 0, so we can apply L'Hopital's rule. So we have the limit as x approaches 0 of the derivative of 1 is 0, the derivative of cosine is negative sine, but there's a negative there, so it's negative sine x, which of course those are going to cancel out and just give me a sine x on the top, or the numerator. The derivative of sine is cosine, and I could find the derivative right, or I could let x approach 0 right now, but just to rewrite it, sine over cosine is tangent. So we have the limit as x approaches infinity of the tangent of x, and if you remember what your tangent function looks like, it comes through sort of like this and passes through the origin and goes to infinity as you approach pi over 2 from the what would be left, and approaches negative infinity as you approach negative pi over 2 from the right. But I don't care about approaching pi over 2 or any form of it. I just want to approach 0, and the tangent of 0 is equal to 0. And that is the end of my last example. I'm Mr. Tarrou. Go do your homework. Bam! Last form, indeterminate differences. If x is approaching a as